Integration by U substitution. If you're looking at your integral and it looks all chain rule-y or all product rule-y or all quotient rule-y, it's probably not something that you can do straight up. Now I know I can FOIL this guy out a bunch of times and distribute 2x, but what fun is that? It's not. So this is what you do. You look at the two functions that you have, 2x and x squared plus 1. And you try to find something that looks like its derivative is floating around. It looks like x squared plus 1's derivative is floating around over here. So whatever looks like its derivative is floating around, you're going to call it u. So u is going to equal x squared plus 1. Take the derivative of that. du dx is going to be the derivative of x squared, which is 2x plus 1, which is nothing. Now, this is how I do it, and I know different teachers do it differently, but this is how I do it. I like to multiply both sides and divide both sides by the dx and the 2x respectively and simultaneously. So what you get would be du over 2x equals dx. Now what I do is I replace what I called u and I take this new dx and plug that in as well and integrate with respect to u. So I have the integral of 2x, x squared plus 1 is u, so u, to the third, and dx is now du over 2x. And if you're like, whoa, 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 how am I going to pull this off? Check this out. The 2x and the 2x cancel each other out. So now we're going to take the integral of u to the third du. The integral of u to the third is going to be 1 over 3 plus 1, which is 1/4, u to the 3 plus 1, which is to the fourth, and I'm going to attach a plus c there. Now I'm not done, because my original problem didn't contain u. I called u x squared plus 1, so I need to plug back in x squared plus 1, so I get 1/4 x squared plus 1 to the fourth power plus c, which is going to be b. All right? U substitution. Fun, 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 fun for the whole family. Evaluate the integral e to the 3x dx. Now this looks very chain rule-y. And when you integrate something that looks like chain rule, you have to think u substitution. So what you do is you choose a u that appears to have its derivative or something close to it lingering around. Well, there's not many choices here. 3x is going to be my u. So I'm going to call u 3x because when I take the derivative of 3 to the x, or 3x, my x goes away. So take the derivative of u, so du dx equals regular 3. I like to simultaneously flip-flop the dx and the 3, so du over 3 equals dx. And now what I could do is I could take that guy, and the fact that I have that guy, and plug a bunch of stuff in. All right, I called 3x u, so the integral of e to the u, and I called dx du over 3. And now all is fair. If I wanted to, I can rip out a 1/3, so I have the integral of e to the u du. The integral of e to the u is just e to the u, so 1/3 e to the u. Don't forget your arbitrary c, that's got to linger there. And I'm not going to circle this because u is not in the original problem. So I have to bring back the fact that I called u 3x. So this becomes 1/3 e to the 3x plus c, which is going to be a. Evaluate the integral of 2x over x squared plus 1 dx. Well, this looks like quotient rule, but there's no such thing as quotient rule for integration. So what we do is we use u substitution. We choose a u that looks like its derivative is lingering around. It looks like the derivative of x squared plus 1 is lingering around up here, so I'm going to let u equal x squared plus 1. Now, take the derivative of that. du dx is going to equal 2x plus nothing. Flip-flop the dx and the 2x, and you get du over 2x equals dx. Now I can take what I have right here, I could take what I said right here, and I can take what I found out here and put it all together. The integral of 2x over regular u dx becomes du over 2x, and oh happy day, the 2x's cancel out. So that leaves me with the integral of 1 over u du. The integral of 1 over u du is ln of u. Don't forget your arbitrary plus c. Now, I can't just circle this because u was not in the original problem. I called u x squared plus 1. So I have to substitute back in x squared plus 1 into u, and I have ln of x squared plus 1 plus c. My answer is going to be A for this one. Pretty exciting stuff. Evaluate the integral from 0 to 3 of 2x over the square root of 9 minus x squared. Well, this looks like quotient rule and chain rule mixed into one whole terrible problem. What you do if you have something like this for integration is you choose a u that looks like its derivative is somewhat lingering around. It looks like if I take the derivative of the stuff inside the square root, I get something awfully close to 2x. So I'm going to let u equal 9 minus x squared. Take the derivative of that, du dx is going to equal negative 2x. Flip-flop the dx and the negative 2, and you get du over negative 2x equals dx. Now let's take this guy and substitute all this stuff and do some integrating with respect to u. Now keep in mind, my limits of integration are still 0 and 3, but those happen to be with the x values, not with these brand new u values. Okay, so I'm going to write out 2x over the square root of u, and then dx becomes du over negative 2x. Oh, happy day, the 2x crosses out. I can bring out this whole negative. Now, while I'm at it, this is what I have now, and it's not pretty. I don't like that. So I'm going to kill two birds with one stone right here. Okay, I'm going to move that upstairs and call it u to the negative 1/2. U to the negative 1/2 du. All right, now my limits of integration are still 0 and 3. I can't forget that. And again, those have to do with x, not with u. We'll deal with that when we have to deal with that. Negative is lingering. Okay, you are going to be 1 over negative 1/2 plus 1, which is a positive 1/2, u to the negative 1/2 plus 1, which is positive 1/2. My limits of integration are still going to be 0 and 3, but with the x's. Okay, so let's clean this up a little bit. Let's bring that 1 over 2, flip it and multiply it to the top to get you negative 2. Let's rewrite this back as the square root of u, with my limits of integration being 0 and 3. But again, my limits of integration are 0 and 3 for the x, not the u. What does that mean? I have to substitute that guy back in for u. So that's going to look like negative 2 times the square root of 9 minus x squared with limits of integration at 0 and 3. This is where we do the whole antiderivative of b minus antiderivative of a thing and set up my brackets and do negative 2 square root 9 minus 3 squared, like that, minus bracket negative 2 square root 9 minus 0 squared bracket. The left one becomes negative 2. Probably should move that out there. Negative 2 square root of 0. Big square root, little number. Minus negative 2 square root of 9 minus 0. So you just completely go away. And we have a double negative, 2 times 3, which becomes positive 6. Interesting problem. I like it. Evaluate the integral between 0 and pi over 2 of sine 2x dx. Now, whenever you see something that looks like chain rule, you are thinking u substitution. All right, we are going to let u equal 2x here because taking the derivative of that leaves no x's, and that makes life easy. So du dx is going to be just 2. Swap the dx into 2 to make it du over 2 equals dx. Now we could take this guy, this guy, this guy, put some stuff together, and do some integrating with respect to u. So 0, pi over 2, okay? Sine is still sine, but now it's of u. Dx now becomes du over 2, right? What I can do is I can rip out a half. So a half of the integral between pi over 2 of sine u du. Okay, the derivative of sine is, careful, negative cosine u, right? That 1/2 is still lingering. Now my limits of integration are 0 and pi over 2, but remember this 0 and that pi over 2 goes with the original problem where it's x is e0 and x is pi over 2. So I have to substitute 2x back into u. So this becomes 1/2 negative cosine 2x, and now we're cooking with gas. Okay, limits of integration, let's do the whole thing where we make a big bracket. I have 1/2 negative cosine of 2 times pi over 2, close it, bracket it, minus 1/2 bracket negative cosine 2 times 0, close it, bracket it. Okay, you become, I really don't need that first bracket anymore, 1/2 times negative cosine of regular pi minus 1/2 times negative cosine of nothing. Cosine of pi is -1. So negative cosine of pi is +1 minus 1/2. Negative cosine of 0, well, cosine of 0 is 1, so negative cosine of 0 is going to be -1. So we have 1/2, double negative plus 1/2, which last time I checked gives us a whole. And that's what we get. Tricky. Fun. Evaluate the indefinite integral of 4x e to the x squared. So this looks like chain rule stuff. And whenever you're integrating stuff that looks like chain rule stuff, you have to pick a u value that looks like its derivative or something awfully close to it is lingering. If I let u equal x squared and take the derivative of x squared, I get 2x, which is close to 4x. So u is going to be x squared here. Take the derivative of that, du dx is going to equal 2x. Flip-flop the dx and the 2x to get du over 2x equals dx. All right, let's combine some stuff, put some stuff together. We have the integral of 4x e to the, let me see, u now. Instead of dx, I have du over 2x. Well, this is nice. The x's cancel out, which it needs to do. And then 4 over 2 simplifies out to a 2, and we'll put the 2 out here. So I have 2 times the integral of e to the u du. The integral of e to the u is e to the u, so 2 e to the u plus some arbitrary c. I'm not going to circle this, though, because originally I didn't have a u. I had x squared, so I have to substitute back in x squared. So 2e to the x squared plus some arbitrary c. And that'll do it. Evaluate the integral of the cosine of the ln of 4x over x dx. Well, we have stuff living inside this cosine, and that stuff happens to be ln of 4x, so let's let that be my u because we're doing integration by u substitution. So u is ln of 4x. The derivative is going to involve chain rule. No big deal. Take the derivative of the outside, which is 1 over stuff, keep the inside, but then multiply everything by the derivative of the inside, which is 4. So the 4 comes up here. 4 over 4 simplifies to 1 over x. Easy peasy. Let's take that guy, du dx equals 1 over x, do some cross multiplying and find out that we get x du equals dx. Now let's take this guy right here, this guy right here, this guy right here, and put some stuff together. We have the integral of cosine of, I called ln of 4xu, so cosine of u over x. Instead of dx, I'm calling it x du. Oh, how nice! The x's will cancel out. Oh, isn't that lovely? So now I'm left with the integral of cosine u du. The integral of cosine is sine, so sine u plus some arbitrary c. And since I wasn't given u to start out the problem, I have to plug ln of 4x back in for u. So I have sine of ln of 4x, close it, plus c, and that ought to do it. Evaluate the integral of x squared over, in parentheses, 1 plus x cubed. All of it is squared. Well, when you see problems like this, you're thinking chain rule-y, quotient rule-y stuff. And when you do that, you use u substitution. So I'm always going to let u equal something that looks like its derivative is floating around. Okay, if I take the derivative of x cubed, it looks like x squared is floating around, so I'm going to have 1 plus x cubed be my u. You take the derivative of that, du dx is going to equal 1 goes away, 3x squared. And then you do the old flip-flop with dx and 3x squared, giving you du over 3x squared equals dx. Now you take this guy, you take that guy, you take the original, you do some flippy-floppy, you do some substitution stuff. X squared is still lingering, but now we have u squared on the bottom because I replaced 1 plus x cubed with u, so u squared. And I'm going to replace dx with du over 3x squared, so du over 3x squared. So now we're integrating with respect to u. The problem is we have x squareds lingering. Not anymore. Let's rip out a 1/3, all right? So I have 1/3 integral of 1 over u squared du. Now, I don't like the way that looks, so let's rewrite that as 1/3 times the integral of u to the negative second power du. So when we integrate that, okay, we have 1/3 lingering, 1 plus negative 2 plus 1, u to the negative 2 plus 1. Since this is a indefinite, we're going to keep that arbitrary c kind of hanging out there. This becomes 1/3 times 1 over negative 1, so negative u to the negative 1 plus c. All right, so cleaning this up just a teensy bit. All right, we have negative 1/3. And let's drop that u downstairs and make it u to the positive 1 plus c. Am I done? No, sir, because u is not in the original problem. 1 plus x cubed is. So to finish this puppy up, we're going to call this 1 negative, oh boy, 1 over 3 times 1 plus x cubed plus c. And I think that should do it. Fun stuff. Evaluate the integral of e to the x over 4 minus e to the x. All right, well, when I see something like this, I'm thinking, all right, well, this is like quotient rule, and that's no good. So what I have to do is I'm going to let u equal the guy on the bottom. We're doing u substitution. Let u equal the guy on the bottom so that 4 will disappear. All right, so du dx is going to equal, go away, negative e to the x, right? Flip-flop the dx and the negative e to the x, so that will be du over negative e to the x equals dx. So now let's do some replacing. Integral of e to the x over u times du over negative e to the x. So now we're integrating with respect to u. Okay, you go away, you go away. Let's bring a negative out front. So I have the integral of 1 over u du, which becomes integral of 1 over u is ln of u, so negative ln of u plus that arbitrary c, because this is indefinite. U originally was 4 minus e to the x, so to wrap this guy up, we are going to have negative ln of 4 minus e to the x plus c, and that's our guy, baby. Someone call the National Transportation Authority, because this is going to be a train wreck. Let's let u equal everything underneath that cube root. U equals x cubed plus 3x squared plus 4. So du dx is going to be 3x squared plus 6x plus nothing. Do the old flip-flop where you're going to replace dx and that guy, so du over 3x squared plus 6x is going to equal dx. All right? Now, let's take this fella up here, rewrite it out, and replace, well, first off, x squared plus 2x, nothing happens. Okay? That's going to be over the cubed root of u. And then what I'm going to do is I'm going to write out, instead of dx, du over that. But while I'm at it, because I see some familiarity here, I'm going to rip out a 3. Okay, so I'm going to rip out a 3, leaving me with no way. X squared plus 2x. That allows these guys to cancel out. So let's do a couple things as we rewrite a bunch of stuff up here. Okay, we have the integral between 0 and 1. All right, why don't I pull out that 3 on the bottom, so that leaves me with 1/3 out in front. You're gone. Why don't I kill 2 birds with 1 stone? I'm going to move that upstairs. Make the exponent, so right now the exponent down there would be this, but if I move it upstairs, now it's going to look like this. Du. So now I'm going to integrate with respect to u. So 1/3 is still going to linger. All right, 1/3 is still going to linger out there. This is going to be 1 over 1 minus 1/3, which is 2/3, u to the 1 minus 1/3, which is 2/3, and I still have those limits of integration, but they have to do with x of 0 to 1. So I've got quite a ways to go before I'm super happy with what I have. All right, quite a ways to go. Let me, in fact, split this into 2 screens so I don't make this look worse than it's going to, because this is going to be a mess. All right, 1/3 is still out there. Okay, 1 over 2/3 is 3/2. That'll be nice because you guys cancel out. I'm going to plug that back in for u. Okay, so that's going to be x cubed plus 3x squared plus 4. And that's still going to be to the 2/3, right? With my limits of 1 and 0. So after cleaning all of that, I get 1/2. Okay, let's turn this back into the cube root of x cubed plus 3x squared plus 4. Actually, it's 1/2. Oh, boy. Oh, that would have been close. Squared. Limits 0 and 1. All right, so time to do some gross math. Plugging in my limits is going to be 1/2 cube root of 1 cubed plus 3 times 1 squared plus 4, all of that squared, minus 1/2 times the cube root of 0 cubed plus 3 times 0 squared plus 4, and then close all of that. So you become 1/2 times the cube root. Let's see if we can do a little bit. 1 plus 3 plus 4 is 8, so the cube root of 64 minus 1/2 the cube root of, another mistake was almost made. 0, 0, and 4. 4 squared is a fun game, but it's also 16. So you become, the cube root of 64 is actually 4. 1/2 times 4. minus 1/2 times, I can't do anything, but I can pull out a 2, so the cube root of 2, I could do that. And this becomes 2 minus u cancel out the cube root of 2. So, not the prettiest problem on the planet. But yeah, that's how you would do it. Fun stuff.